Hello everyone, welcome to our project. The name of our project is UART design using Verilog for FPGA implementation. This project is a part of our course EEE304 Digital Electronics Laboratory. This project is presented to you by Ilias Ahmad, Puspita Mobarak, Mohammad Al-Amin, Mohammad Al Hosan, and myself Dipto Archishman Saha. Let us dive deeper into this project. Firstly, our objectives. Our objective is to develop Verilog modules for UART transmitter and receiver and evaluate the functionality of the modules using timing diagram and test bench. Furthermore, we want to apply our modules in hardware using FPGA or CPLD. Let us have a brief introduction. Firstly, what is UART? UART means Universal Asynchronous Receiver Transmitter. This is a physical circuit in a microcontroller or in a standalone IC whose purpose is to transmit and receive serial data. Now we know that our data is basically in parallel form like 8 bits of data. So the transmitter will convert that parallel data into serial and transmit it serially. And then what the receiver will do is that it will convert that serial data back into parallel and show it in the output. What is baud rate? Baud rate is the specific frequency at which UART reads the incoming data bits. It is actually the measure of the data transfer speed, which is expressed in bits per second. Both UARTs, that is the transmitter and the receiver, must operate at the same baud rate, which is determined by the baud rate generator. Now, from the name, we have seen that it is asynchronous data transmission. That means there is no clock signal required to synchronize the transmitter and receiver UARTs. The synchronization process is actually conducted by start bits and stop bits. Start bit indicates the start of data transmission and stop bit indicates the end. Now, a typical data packet consists of one start bit, 8 data bits, a parity bit, and 2 stop bits that we have used here. So, we have adopted finite state machine to construct our program. The finite state machine means a sequential circuit which has a limited number of states, where the machine can be in exactly one state at a time. The machine can change its state according to some conditions and inputs. This change is known as transition, and the number of states that a finite state machine can be in is known as modulus. Finite state machine consists of state register and combinational logic, and the state diagram is actually a directed graph or a diagram where the nodes represent internal states and the arrows represent state transition. Here is a state diagram for our UART transmitter. So we see that there are 6 states. S0 means idle, S1 means start bit, S2 means data bit, S3 means parity bit, and S4 and S5 means the last stop bits. So what are LA, LB, and LC? LA is the serial bit, LB is the bit that indicates if the system is active or not, and LC means the bit which indicates if the process is completed or not. So in S0, that is the idle state, there is LA equal to 1, that means the serial bit is 1. When there will be start bit, bit 0 will be sent, that means LA is equal to 0. Now, when there will be a transition between S0 and S1 is that when there will be ITX-DV equal to 1. Because when ITX-DV is 0, it actually remains in the idle state. ITX-DV actually indicates reset. So, from idle state, we go to the start state, and then afterwards it goes to the data bit state. In data bit state, the data from LSB to MSB is transmitted. Total 8 bits is transmitted. So we have given a condition I less than 8. That means as long as 8 bits are not sent, the state will remain S2. When 8 bits are sent, then the state transition occurs from S2 to S3. And in S3, the parity bit is sent. So the parity bit is 0 if there are even number of ones. Otherwise, for odd number of ones, the parity is 1. And then we go to the stop bit Here LB is equal to 0, that means the system is no more active, and LC equal to 1 means the job is completed. These are our transmitter code and receiver code. Now I will explain part by part in a bit detail. So the simulation for the transmitter part, here we can see the case idle in the code. So for the idle case, if the ITX DV, which is actually the reset, is equal to 1, then the process will start, and from idle bit it will go to the start bit case. Otherwise, the system will stay in idle state. Now let us check the next case, that is the start bit. So in this case, here what we have seen, that we have sent OTX serial equal to 0. This means the start bit is 0, and it will wait certain clock cycles for finishing, and then afterwards it will execute the data bit case. Now for the data bit case, here we are also checking the parity using this line, RTX parity is equal to RTX parity XOR RTX data. So in this case, the parity is updated for each bit, and later on after the data is transmitted, we will check its use. And here we have seen that the bit index is also updated because we have to execute data bit for 8 bits. When the 8 bit is completed, it will move to the next state, but until then it will execute the data bit state. And here we are showing the parity bit case. So now we have stored the parity in RTX parity, and in this case we have shown the serial bit is equal to the parity bit, and it will again wait certain clock cycles to finish, and then it will move to the next state, which is the stop bit. The stop bit is 1, which is shown here, OTX equal to 1, and then it will execute the cleanup, that is actually another stop bit, and then the process is completed for the transmitter part. Now let me show the timing diagram. Here the bit sequence that is sent is 1010, 1101, and when it will be sent from LSB to MSB, then firstly it will send an idle bit, that is 0. Here we can see that OTX serial is 0 here, and then it will execute 10110101 serially from LSB to MSB. So here we have found that 10110101, and then it will send the parity bit, which is odd parity, that means it will send 1. So the odd parity is also sent, and then 2 stop bits are sent here. Now let me show the pin planner. Here we can see that the 7, 8, 9, it is showing the bit index, and then 10, 11, 12, 30, it means active, done, parity, and serial. Let me explain it case by case later in the output. So now for idle case, we have seen that the serial bit is 1. So here the L7 is lighten up. Now the start bit, L7 has become 0, and L4 has become 1. That means the system is active. Now bit 1 is sent, bit 1 is 1, so L7 equal to 1. L6 is also equal to 1 because the parity is now odd. And L4 is equal to 1 means the system is active. And L3 is indicating 1, and L2, L1 is indicating 0. That means L1, L2, L3 is equal to 0, 0, 1, which indicates the bit index. Now for the second bit, here we have seen that the bit index is being indicated 0, 1, 0, which shows the second bit, and L7 is equal to 0, L6 is equal to 1 because the parity is still 1, and L4 is equal to 1 means the system is active. Let us quickly look at the remaining cases. Bit 3 equal to 1 means L7 equal to 1, and L1, L2, L3 is indicating the bit indexes. The parity is now 0 because we have achieved 2 ones. Here we have achieved another one, so the parity is being changed. L7 remains 1, and L1, L2, L3 indicates 1, 0, 0. Now the next case 1, 0, 1, and L7 equal to 0. And the next case L7 equal 1, L1, L2, L3 equal 1, 1, 0. The next case 1, 1, 1, and the last case here, this is the last bit. So L1, L2, L3 is indicating again 0, and L7 equal to 1 and L6 is equal to 1 because we have sent 5 ones, that is odd parity. And later we show the parity bit. So this is unchanged. And lastly, the stop bit. The stop bit, so L4 has now become 0 because the system is no more active, and L5 has become 1. That means the process is completed. So here we have shown the transmitter part. Now I'm going to show the receiver part. So here also there are many cases. Among them, the first case is the idle case. Now the system will actually remain in high state, but when it will receive a start bit, that is the low state, then it will conduct a state transition. So it will move from idle state to start state. So if it receives a 0, that is the start bit, then it moves to the next state as shown here. So the next step will be, it will check the middle of the start bit because there can be a faulty signal of 0. So when it checks the middle of the start bit and still finds 0, then it actually is satisfied that the start bit is valid. Then the start bit is since valid, then it will move to the next state, that is the data bit. So we have shown the data bit state here, and in the data bit it also stays certain clock cycles, and the data bit is received here, that is the RRX byte, and R bit index is equal to RRX data. We are also keeping the count of the bit index because we have to receive 8 bits. And again there is the RRX parity here. RRX parity is equal to RRX parity XOR RRX data. Why we are doing the XOR? We are doing the XOR to keep the count of the parity. Here we are keeping the count of the parity, and again at the same time we will also check the received parity bit. Now if the received parity bit and my parity count both are same, that means there is no error. But if the parity count is differing from the received parity bit, then this means there is error. So here RRX error is indicating this thing. If the XOR is 1, then there is error. And lastly, we have shown the stop bit and cleanup bit. There means 2 stop bit. Now let me receive the bit sequence of 8 ones. So here we have shown that the parity is changing each time we have received a 1, and the bits are also received correctly. Here 1, 1, 1, 1, and serially all the ones are received from LSB to MSB. Now, here we have seen there are 8 ones, that is even number of ones. That means parity should be 0. But if we send the parity bit also equal to 1, then there is an error, right? So the error is also indicated here. ORX error, here it is actually showing high state. Here is the pin planner. So the bits from MSB to LSB are shown from 7 to 14, and then pin 17, 18, 19, 20 indicates that is the active, that is the valid state, there is an error, and there is the parity. Now let me explain case by case. When the channel is inactive, then it will receive the start bit and then it will become active in the next case. As we have shown here, L9 has lightened up. That means the system is now active and it is receiving the start bit. Now, when it receives the first bit, here we have seen that L8 has lightened up, and L12, this is the parity has become odd. In the next case, the next one is received, parity has become even, it has changed as we have shown in the timing diagram. The next case, one more one is received, the parity is changing. Again, one is received and the parity has changed. Then bit 5, bit 6, bit 7, and bit 8. Here we have shown that the parity has changed bit by bit, case by case. Now let us show the next case. Okay, just a minute. Yes, parity bit. Okay, the parity bit is being sent 1 here. Okay, so since the parity bit is 1, but our checked parity is 0, so the error bit will also show 1. Here L11 is lightening up, so that means there is error. And in the next case, let us see, the stop bit is equal to 1. So The stop bit indicates process is complete, so L10 has lightened up. Here we are showing the test bench. In the test bench, firstly, we created some instances, and we have also declared some parameter and raise type, wire type variable to work on the instances. And we have indicated a task, that is UART write byte. It will write an input byte and serialize it. So using this task, we will actually check the receiver, which we will show in the next slide. Here we have instantiated the UART receiver and transmitter, and this is our main testing. So here we have written a task before. So UART write byte, here we are actually writing 8-bit data, and we will check the receiver using it. And in this main testing code, here we have checked the transmitter, and here we have also checked the receiver. So, and we have also checked the parity of it. Now, when we write the 8-bit data 2F, that means it will actually have 5 ones in it. The parity is odd. And here we have shown the result, that is the transmission, the byte is successfully sent. And in the receiving end, also the received byte is successfully received, and the parity is 1. That means the parity is actually correct. So receiver test has also passed, and the test bench has successfully tested our program. Credits. We especially thank our course teacher, Dr. Sajid Mohammad Choudhury, for his lecture slides and helpful insights. These are our references that we followed. Thank you so much.
সো এখানে আমরা একটা ইউআরটি ট্রান্সমিটার ইমপ্লিমেন্ট করার চেষ্টা করতেছি। এই ইউআরটি ট্রান্সমিটারে আমরা কি করব, এই প্যারালে যে ডাটাটা আছে এটা হচ্ছে আমরা সিরিয়ালি আউটপুট আর কি দেখাবো। এই যে এটা হচ্ছে আমার সিরিয়াল আউটপুটটা। সো এই সিরিয়াল আউটপুটটা হচ্ছে গিয়ে 0 আর 1 হবে। অ্যান্ড আমরা জানি আইডল স্টেটে কি হয়, আইডল স্টেটে আমার আউটপুটটা 1 থাকে। এই জন্য আমি এই যে রিসেট বাটনটা এখনো ক্লিক করে নিই, তো আমার আইডল স্টেটে জিনিসটা যাচ্ছে। সো আমি যতই ক্লক দিচ্ছি আমার এটা 1ই থাকতেছে। অ্যান্ড এখন আমি রিসেট বাটনটা দিব, এখন আমি দেখি কি হয়। এই যে স্টার্ট হয়ে গেল, তো আমার সিস্টেমটা স্টার্ট হয়েছে, আর আমার আউটপুট বিটটা হচ্ছে 0, কারণ আমার স্টার্ট বিটটা ইউজুয়ালি 0 থাকে। দেন আমি ডাটা বিটটা পাঠাবো। এই যে ডাটা বিট, আমার ফার্স্ট ডাটা বিটটা হচ্ছে 1, সো এটা যাচ্ছে। এখন আমার বিট ইন্ডেক্সটা একটু পরে আপডেট হবে। এই যে আমার বিট ইন্ডেক্সটা আপডেট হলো, প্যারিটিটাও আপডেট হলো। এখন আমরা সেকেন্ডটাতে দেখতে পাচ্ছি যে আমার 0 1 0 মানে ইন্ডেক্স দেখাচ্ছে 0 2, অ্যান্ড আমার হচ্ছে আউটপুটটা হচ্ছে 0, প্যারিটিটাও হচ্ছে কি 1ই আছে। দেন আমার থার্ড বিটটা 1, প্যারিটি এখন 0 হয়ে গেল, অ্যান্ড আমার হচ্ছে গিয়ে বিট ইন্ডেক্স 3 এটা দেখাচ্ছে। এখন 4 বিট হচ্ছে 0, প্যারিটিও হচ্ছে গিয়ে 0। ফিফথ বিটটাও 0, 6 বিটটা আমার 1 হবে, এই যে 1, অ্যান্ড বিট ইন্ডেক্স প্যারিটি সব চেঞ্জ হলো। এই যে আমার এখন 6 বিটে আছে। নাও 7 বিট, এই যে লাস্ট বিটটা 1, প্যারিটি চেঞ্জ হয়ে গেল। সো আমার আলটিমেটলি প্যারিটি কত, 1 2 3 4 5টা 1 আছে, অড প্যারিটি তাহলে। দেন আমি প্যারিটি বিটটা পাঠাই। এই যে প্যারিটি বিটটা 1, মানে আমার পুরো সিস্টেমটা অ্যাকচুয়ালি আনচেঞ্জ আছে এই অবস্থায়। অ্যান্ড এখন আমার স্টপ বিটটা পাঠাবো। এই যে স্টপ বিটটা গেল, অ্যান্ড আমার যেহেতু সিস্টেমটা কমপ্লিট হয়ে গেছে, সো এই অ্যাক্টিভটা এখন আমার ইনঅ্যাক্টিভ হয়ে গেছে, আর এই যে স্টপ বিটটা গেছে এটা দেখাচ্ছে। অ্যান্ড দেন ফাইনালি হচ্ছে গিয়ে আমার আইডল স্টেটে চলে গেছিল। সো এখানে হচ্ছে আমরা রিসিভারে আমরা এই 8 বিট হচ্ছে আমরা প্যারালাল আছে, এটা আমরা সিরিয়ালি পাঠাবো। আগে হচ্ছে একটা স্টার্ট বিট যাবে, দেন 8টা ডাটা বিট যাবে। 8টা ডাটা বিটের মধ্যে হচ্ছে গিয়ে 1, দেন 4টা 0, দেন 3টা 1। সো আমরা ফার্স্টে স্টার্ট বিটটা পাঠাই, এই যে 0 যেটা আছে পাঠাই। এবার 1 পাঠাই, এবার আবার 0, আবার 0, আবার 0, আবার 0, আবার 1, আবার 1, আবার 1। দেন প্যারিটি পাঠাবো, প্যারিটিটা আমি 1 পাঠাই। ওকে, সো এখন আমি আপাতত যেটা করলাম সেটা হচ্ছে স্টার্ট বিটে 0 পাঠাইলাম, দেন একটা 1 পাঠাইলাম, দেন 4টা 0 পাঠাইলাম, দেন আবার 3টা 1 পাঠাইলাম, দেন একটা প্যারিটি পাঠাইলাম। এটা আমি পরের সাইকেলে দেখবো যে কী হয়। সো এখন আমার এই যে 1 দেন 4টা 0 দেন 3টা 1 এটা কিন্তু আসছে আমার ঠিকঠাক, অ্যান্ড সিস্টেমটা অ্যাক্টিভ আছে এটা বোঝাচ্ছে। অ্যান্ড আমি প্যারিটি যেহেতু 1 পাঠাইছি, সো আমার কিন্তু একটা এরর আসা উচিত, কারণ আমার প্যারিটি অ্যাকচুয়ালি ইভেন, বাট আমি পাঠাইছি অড প্যারিটি। এই যে এররটা কিন্তু আসছে। সো আমার এখন পর্যন্ত সিস্টেমটা পুরোপুরি ঠিক আছে। অ্যান্ড এই যে আমি এখানে দেখতে পাচ্ছি আমার ট্রান্সলেশনটা কমপ্লিট হয়েছে।